So share the screen and let me know if this screen is visible.
Yes, sir.
Yes.
It's visible, sir.
Okay, great. Thank you. So let's just have a quick review of what we were doing last week. So we started with, of course, probability and statistics. I mentioned regarding the classical definition of probability and also that the frequentist one. There is Bayesian definition of probability which is related to our subjective cognizance or degree of belief. But ultimately, Kolmogorov in 1900s put together everything in terms of the three axioms which we discussed. And in that, it defines that whatever definition of probability has to come should or must obey these three axioms. So that's the axiomatic definition of the probability, where we are assigning a real number greater than or equal to 0, total probability of a sample space was 1, and probability of the union of two disjoint events A union B is equal to PA plus PB. Rest all of the properties can be derived from these three axioms. We discussed conditional probability, independence of the event. Two events are said to be independent if the P A intersection B can be written as PA times PB. Please remember that definition forever because that's something which will be used. Total probability theorem and the Bayes theorem, they give nice extension because now with this degree of belief added in the Bayesian definition, this can be used for variety of practical purposes and we used for detection of a particle using a detector. So that was one of the examples which we did. And towards the end, we were doing combinatorics, permutation and combination. So of course, it is more than permutation and combination. We considered four cases. And towards the end, I was asking what's the probability for the case when sampling is done with replacement. However, ordering is not important. And by this time, did you try to figure out, or I mean, one of the answers was already correct on that day. So can somebody say it to finish it off? So sampling without replacement. Oh, sorry. Sampling with replacement and ordering does not matter.
N plus K minus 1 CK.
Great. Yeah, this is, I mean, if you start making it n plus k minus 1 c k. So this is the right one, and somebody actually said it towards the end of the class. So it's absolutely fine. Except that, please check that this formula, I mean, it takes some time to figure out that this will be the formula. Just by looking at the example, the one which I gave may not be that, I mean, fruitful in terms of arriving at a formula. Although, of course, you will get the result from this one. But how will you get this formula? That's an interesting one. Now, when you talk about the combinatorics, please see that statistical mechanics, particularly microcanonical ensemble. Does somebody remember the definition of entropy in statistical mechanics? Boltzmann definition of entropy, that is what we call that. Okay, Boltzmann constant, omega, where omega
AB log
was
of microstate numbers.
Sir,
number of microstates,
Thermodynamic.
right?
Number of micros.
So number of microstates one used to get by doing what? By putting the particles in the energy levels. Remember that the microstates definition have to have the density of states one and then the some sort of a distribution function. So this number of microstates calculation in the microcanonical ensemble, be it classical or quantum, then we talk about the Bose-Einstein or the Fermi-Dirac one. That is all coming from the definition of the probability itself. That how do you put, let's say, number of particles in certain energy levels. So whole branch of statistical mechanics, if you can think of, because it is about the statistical distribution of particles together, that is coming from this mathematical idea of the probability and statistics. Okay, today I will continue to build on the ideas so that we will have some crystallized definitions and understanding of probability, and you will figure out that it will be more important. I mean, in general, even though we are doing calculations without even recognizing that we are basically doing calculations coming from the probability and statistics. So for that, let me first define a variable, what we call as the random variable. Does somebody know what is a random variable? Any idea of the word random variable? Any idea of the word variable? Because that's what we use all the time.
So
Any
a variable
quantity
is
which change.
contains different values. You can say.
Yeah, reasonable that any quantity which takes different values rather than taking one. I mean, this is what we are doing from our mathematics class when we started defining x or y as variable. Now, how will we think of random variable? So let's just think about this. A sample space, a simple one, toss of a coin. So it sample space consists of a head and tail. Now, random variable is basically say that instead of talking about these qualitative names h and t, we will assign some numerical value to each outcome. So instead of saying h or t as the head or the tail, we will assign a variable such that that variable will take some numerical value. So maybe if we say, let's define random variable to be the number of head in the toss of a coin, then you will say there exists a random variable which will take a value 1 when head comes, and this random variable can take a value 0 when tail will come. So instead of talking about the sample space in terms of h and t, suddenly you will start talking about a variable which is having a numerical value, a value which can be either 0 or 1. So why this would be important? This would be important because mathematically when you are going to solve problems, it will always be easy to work with numerical values rather than thinking about some qualitative names or references. So in effect, what is random variable? I mean, if you go for a technical definition, then it is something like this. So I have a sample space
Good
and
morning,
I have
sir.
good morning, but I would suggest that if I start teaching, then please do not say good morning in between because it basically breaks the flow. Thank you.
Okay, sir. Thank you, sir.
Yeah, thank you. Right. And that means what? That means that if there is a sample space S and there exists a sample point, then I project that sample point onto a real axis so that it takes a numerical value. So now if I take something from one space to another space, what kind of thing do we call that? If I take something from one space and I project it on another space.
Linear transformation.
One. So linear transformation is a very generalized name where we have to use the word linearity and then we use the word transformation. Sure, but even more general, that is what you are using since
A
7th or
mapping.
8th class. Mapping, right?
Mapping.
And generally, how do we call mapping? I mean, we already see mapping is function, mapping is functional, mapping is operator. What I am doing right now, I am taking one object from S and I am projecting it on another one. What is the value which this guy is getting? Is it a number or a vector?
Number.
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 So
Number.
what happens if an argument is such that it is going to give me a number? This is generally what we call as the simplest
Function.
one, right? So random variable, even though the word is random variable, but it is a real valued function. And what is the job of this real valued function? The job of the real valued function is simple. That this guy takes an object from a sample space and project it or map it onto the real number space. So that we can define something like x of h is equal to 1. Now, why it is called random? As the name suggests, that I do not know what outcome is going to be there in a particular trial, which means that this variable, even though the word variable is already there, but this variable takes random values. That's what the idea is. Now, to correlate it with what we are doing in, for example, quantum mechanics, let's think about a hydrogen atom. So there exists, let's say, nucleus. So what does the hydrogen atom nucleus contain?
Proton.
How many?
One.
One.
One proton.
One.
What
One
about the
proton.
neutrons?
Zero
Neutron.
neutron.
No, zero
What
No
about
Zero.
neutrons.
electrons beyond the nucleus?
One.
One.
At
One.
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 okay, one. So what about the position of this electron outside the nucleus? Electron cannot reside inside the nucleus. You have given sufficient arguments. I am sure that you are going to give the arguments again in your nuclear physics lab class. But what about the possibility of this electron outside the nucleus? Where does it go? Is it very close to the nucleus? Is it very far off from the nucleus? Is it somewhere in between the nucleus? Or what? Anybody? Where does the electron reside?
Sir, it's
Close to the
probabilistic,
nucleus
sir.
only.
It
Close
can
to the
reside anywhere.
nucleus.
It can reside anywhere. And then what was the Bohr radius? What was the Bohr radius?
0.5
0.53
0.53
Right,
angstrom.
that is the number. What is about the Bohr radius? Why it is called the famous Bohr radius?
Sir, 90% of the probabilities that it will stay inside the Bohr radius. 90 or
It will
99, I don't remember.
Okay, that is something which we should do in the class. But please understand that when Bohr gave the idea of an
He
atom,
was not talking about the Heisenberg uncertainty principle. So he was certain that it will reside in that uh,
right,
distance
right,
from the nucleus.
good. So when Bohr was talking about an atom, it always Bohr tried to mention that electrons exist in certain energy levels. It is true that electrons energy of course is discrete, but electrons in the end we found out it is not in those certain discrete energy level, but there is a probability with which we can find that electron is there on any of the point outside the nucleus, right? Now that means that you can talk about the electron's position from the nucleus as a random variable r, and we can do all the things about the probability from that, because if we know what is the wave function xi1s, which is the ground state electron, n exponential minus r, let's say over a naught, which is what the wave function would be for a ground state electron in that, or hydrogen atom. In that case you can quickly figure out the probability xi star xi and do all the calculations to figure out the things related with the probabilistic nature of this wave function. So probability and statistics that help us in figuring out several problems related with the quantum mechanics, particularly because of the inherent nature of the probability in the quantum mechanics inbuilt. But in that case, what will be the random variable? This r or x, you can say, is the random variable, which is nothing but the distance from the nucleus. So the whole idea is that random variable is some sort of a numerical function or numerical value which we assign to each of the outcome of a probabilistic or a random experiment. And when I call a random experiment, remember it's the outcome of a given trial is random. But we still know the sample space, that all what are the possible values. Yeah. Okay. Random variable itself is not unique. It is up to us to define random variable. So random variable is not unique in any case. So for example, in the toss, x is equal to ht. Somebody else say, oh sir, I want to define random variable as the number of tails. And that is absolutely justified. And in that case, that random variable will take value 0 when it head comes, and this random variable y, this takes the value 1 when tail comes. So it can be anything. But it also gives me another interesting feature, that random variable, just like the case we were doing even in our linear algebra, that I can define it in terms of the discrete and continuous ones. So we are giving a complete description of probability statistics. We come up with a term random variable, a term which is given just to assign numerical value to various outcomes, nothing beyond that. But we are interested in more than that, right? Just like the way we were discussing, there is a probability which is associated with each distance. So somehow we should be able to also think about probability values which a given random variable will give. It's customary to define random variable by capital letters. So x is a random variable which is number of heads, y is a random variable which is number of tails, r is a random variable which is the distance from the nucleus. It's a very customary thing. And the values, the actual value which the random variable takes, that is defined by small letters, small x, small y, small r. So for example, here when I am saying that the number of tails y is a random variable, capital Y is a function, and the value which it is taking 0 or 1, that is generally denoted by 0 y small letter. So small letter y is taking value 0 or 1, which is nothing but for the random variable capital Y. And we will continue to build on that, and wherever you have any confusion, you will ask me. Random variable can be discrete, like the case when I am tossing a coin, rolling a die. In those cases, is of course it's a discrete one, or it can be a continuous one. For example, the distance from the nucleus for this electron, that's a position variable, and position can take any value, and hence that's a continuous one. Can anybody give me any example of another continuous random variable? So one is the position from this.
Speed.
Rate and
So
height
can
measurement.
you define a random variable in that case? Speed means what? What you are talking about? Is the speed governed by probabilistic constraints or distributions, or generally speed is governed by some well-defined one? Think about it, where the experiment has to be random. So just like in the case of quantum mechanics, finding the electron position, there is a probability associated with each point. So speed, where does speed show as a random variable?
Sir, in gases, motion of gases.
Very nice. So it was coming from the statistical mechanics again. I mean, there are two places where you will find plenty of examples. One is quantum mechanics, another is statistical mechanics. So when you did even the Maxwellian or Maxwell-Boltzmann distribution of velocities, what were that? Distribution of velocities of particles, classical collection, which is an ideal gas, having each of the particle has its own velocity, let's say Vx in one direction or Vx, Vy, Vz in three dimension. And that's governed by which distribution?
Maxwell-Boltzmann.
Maxwell
Maxwell-Boltzmann distribution.
Boltzmann.
What is meant by when it is governed by Maxwell-Boltzmann distribution? That each of the velocity value has an associated probability. So it's a random experiment. Again, it is just that we are using several formulae of our probability statistics without even realizing that it is part of that. But it is good that we can use it even without knowing all the things about it. Anyway, so random variable can be classified into discrete, or random variable can be classified into continuous one. So accordingly, there are formulae for calculating the probabilities. So first thing we know now is that there exists a random variable. Now we are interested in just not only the random variable, but what is the probability that this random variable x take. Now this. So we have basically two forms, one for the discrete random variable and another for the continuous random variable. So let's just build on that. So first, so if I talk about discrete random variable, set of all probability values. So I am talking about a set of all values for a given random variable. That is what defines, in the case of discrete random variable, called probability mass function, or PMF. Very trivial concepts, but we do need to know. So let me just define it. So there exists something what we call as the PMF, which is nothing but the probability that a random variable x is going to take value xk. This is what is defined as, sometimes even written as pk, the probability mass function. So I'm just defining a name for associating a probability. I call it probability mass function. And what is probability mass function? There exists a probability with each of the random variable. Now, since it's a discrete one, so k will take discrete values. So just to give an example again, so if x is a random variable, which is number of heads for a toss of a coin, what is the value which random variable can take?
1 and 0.
0 and 1.
Okay, right. Let's write 0 and 1. And what is the probability mass function for that? So
Half
xk
and
is
half.
this. So for a fair coin, this will be half and half. So collection of all possible values, if you just add together, put all of these together, if you can define it for everyone, then these values is what are called the probability mass function. Rather simple concept, nothing more than that. But does this probability mass function have to have or have to obey certain properties?
Yes,
And what are those?
the sum should be equal to 1.
It should be less than equal to.
Right.
Should be
So
positive.
rather simple. Pxk should be greater than or equal to 0, just like the way you are saying that it has to be positive. It's a probability, right? And sum over all k's should be equal to 1,
1.
right? So it's rather simple. Yeah. So probability mass function is what? Probability mass function is something very simple. Probability mass function is nothing but the probability which a random variable is going to take. Good. Definitions continue. There is something called cumulative distribution functions. And you will have question, I mean, you may think about why we are doing things like this. Once we start doing things in this manner, that we associate, first we define a random variable, then we associate probability associated with it in terms of probability mass function or something in the continuous case, then you will see that the different problems in different fields can be put together under a same umbrella. Then you do not need to always think about, oh, if the Maxwell-Boltzmann distribution comes, then what should I do? If the wave function is given, then what should I do to figure out certain quantities? Those will all fall under the same umbrella of probability. So we are just trying to make again, trying to put together our ingredients together so that we will make a recipe which can be useful in variety of cases. Okay, so continuing with our definitions. The second definition, or actually the third one, the first one is the random variable, the second one is the probability mass function, third one is the cumulative distribution function. So as the name suggests, the word cumulative, what does the mean? What is the meaning of the word cumulative?
So which keeps on adding, kind of.
Very good. It is just that, exactly. So it is there in the PMF, we were talking about the probabilities exactly equal to that particular point. Whereas in the case of cumulative distribution function, we talk about the probability less than or equal to certain value. Exactly just like the way you are saying that we are adding the individual probabilities, where xk is less than equal to x. So we talk about the PMF and sometimes we also talk about the cumulative distribution function. We'll do an example just to see how the result come out to be, and it will be very trivial. I'm pretty sure all of you will be able to do it pretty fast. But let's just try to understand the features of this cumulative distribution function. First, it's a non-decreasing function. Non-decreasing function. So what does that mean? Non-decreasing
For
function.
increasing
That it keeps on
As we increase the
increasing as
value
we
of
add the
x,
terms.
So as we keep on increasing the value of x, this function remains either flat or will be greater than the previous one. So f sorry fx1 sorry just a sec. Yeah, fx1 will be strictly less than fx2 if x1 is less than equal to x2. There is a possibility that you may go to higher x, but the function remains flat. And that is the reason why I'm using the word non-decreasing and not the increasing function. Ever increasing function will mean that whenever x1 or x2 is greater than x1, your fx2 has to be strictly greater than fx1. But that's not the case. It may be flat also. What would be f of minus infinity?
0.
This will be 0 because the random variable x, any random variable, which takes the least possible value, that means that there is no probability or the zero probability which is associated with it. And what about the uh, f
1 over
infinity, that is
1.
random
1.
variable 1, which means that you know about this function also, just like the way you know about the PMF. PMF was there between 0 and 1. Similarly, CDF, a function, remains between 0 and 1. Last word I am going to write continuous. And this is something which I will explain by giving my example. Right continuous. Can anybody say anything about this word, right continuous?
So before that, I have a question
Yeah, please go ahead.
from sir. Like as you said that if we keep on adding the values to the
Yes.
function, then
Yes.
the function will either remain flat. So, sir, when we are adding the values, how can the function remain constant?
Yeah, we will see. I mean, see, what I find whenever an abstract concept comes or the definitions come, the best thing is to look at an example which we can understand simply. And if we can decipher the main features from that simple example, then that would give you an idea how it will happen. So I
Yes,
have an
sir.
example coming up immediately after finishing up this word right continuous, and hence I am reserving that. Once you have that example and after that it is still not clear, then you please ask the same question again. Make sense?
Okay, sir. Yeah,
Yeah,
sure,
okay.
sir.
Okay, so right continuous. Can anybody say anything? I mean, we are going to see what it means soon, but can anybody say anything about? I am writing something which is strictly mathematical. The word continuous, it is about the functions, remember? And I am saying it is a right continuous one. So what do you know about a continuity of a function in general? I mean,
Sir,
remember
the
the limits.
limits,
Yeah,
the left hand
The
limit and
graph
the
should
right
come
hand
like
limit will
this.
come out to be same at the point which we are considering.
Limit.
right. In general, whenever we talk about functions, we talk about limit of a function. Now, on a real axis, if you can imagine a real axis just like a line, then we talk about, okay, the limit is coming from the left hand side as well as from the right hand side. If I am saying that something is right continuous, then it means that when I will be approaching it from the right hand side, function looks continuous. But if I approach it from the left hand side, then the function may or may not look continuous. So we will see what it means, but it generally, the concept of continuity, immediately try to think about word limit. And as soon as you start thinking about the limit, think about a real axis where the limit can be approached from the right hand side or from the left hand side. When a function is continuous, in general, we talk about it is continuous when the limit is same from the left hand side as well as from the right hand side. We are saying something as a right continuous cumulative distribution function. So we'll have to specify what it means, and we will see it in this example which is coming up. So let's just understand things from the simple example. Consider example, toss of 3 coins and x be a random variable which is nothing but the number of heads. So toss of 3 fair coins, okay, I should say fair coins, and x be a random variable which is nothing but the number of heads which come in a given toss, which means the 3 coins are tossed together. So question number 1, what values random variable x can take? Question number B,
3, 2, 1, 0.
px, right? I'm pretty sure that you are going to do that pretty fast. Px, fx, and sketch. All of those, px and fx. So yeah, somebody did say that. So what values random variable x can take? That is x is equal to small x. So let's
0,
just
1, 2, and 3.
0, 1, 2, and 3.
2 and
And
3.
what will be the probable? So PMF. So let me use the word PMF, PX. So this is the PMF. What is the probability that 0 heads will come?
1 by
1 by
8.
8.
Okay, is it clear to all of you? Because I'm pretty sure that everybody knows that sample space in general, you can make it HHH, HHT, so on and so forth, up to TTT. And when you have 3 tails coming out, you are putting number of heads to be 0, right? How? So random variable x is equal to 1. That means in the toss, 1 head has to come. So 1 head, and that means 2 tails. 3 by
3 by
8.
8.
Great. What about 2 heads?
3 by
3 by 8.
Great.
3
What
by 8.
about 3 heads?
1 by 8.
1 by 8.
1 by
1
8.
by 8.
Great. And let's just try to write down our CDF also for that. So what is the value for fx equal to 0? So that means now we are talking about probability x less than equal to 0, not 0, but small x, okay?
1 by 8.
So first one,
1 by 8.
1 by 8.
Okay, so let me write down 1 by 8. And by the way, what is the value which this function will be taking just before 0?
0.
Zero.
Okay. Okay. What about f of 1,
Half.
Half.
which is
Half.
by 2.
1 by 8 plus
3
3
by
by 8, which is equal to 4 over 8? Absolutely right, which is half. Very good. What about f of 2?
7 by 8.
7 by 8.
7 by
7 by
7 by 8, that means you are adding the numbers. Absolutely fine. What about this?
1.
1.
1.
1.
Okay. Now I will sketch it and I will discuss the essential features. And okay, just like the way I said, it's piece of cake for most of you. So x first, PMF. This is what is generally plotted. Remember that Maxwell-Boltzmann distribution of velocities. What you are plotting is, okay, that's not a discrete one, but a corresponding one of this discrete probability function as the function of the random variable. Now this random variable can take only discrete values 0, 1, 2, 3. So 1 over 8, let's say 3 over 8, 3 over 8, 1 over 8. So this is what you. Now remember that we have a tendency of joining the points by these lines. I mean, generally we join it by lines. Can we do it in the case of this probability? Is the probability
No, sir.
defined at
Because
any points other than 0, 1, 2, and 3?
No, sir.
No, sir.
No.
No. So please understand one important thing about the discrete random variable, that probability or PMF is defined only at discrete points. There is no way you can say anything about the probability anywhere else. People have the tendency of writing 0 anywhere or not. But please see that when we talk about the probability mass function, which is probability corresponding to discrete random variable, the definition itself is not valid for any points which is not on this 0, 1, 2, and 3. And hence it's a wrong way to depict, even though in the books you will see that there is some sort of a continuous line which is joining these points, but it's wrong. Probability is defined only at discrete points. We must remember that.
Sir?
So yeah, any point, yeah, just any point in between, if somebody asks the probability, say it's an ill-defined quantity there. Answer like that. Yes, please go ahead.
So you said probability is not defined at any other point. So when you ask what will be the probability just before 0?
Yeah, I did not ask the probability. I asked the probability distribution function and continuous cumulative distribution function, and I will come to that. This is what I am going to do next. So you will have to answer in that manner, and that is what interesting thing would be. And that is why CDF, which is a reasonably continuous function, is sometimes used in the discrete variable. Let me just finish off this example and reserve the questions till then. That's only. Fine. I understand your confusion, but at the same time, let me just tell you what happens, why we define these two kind of functions. So let's just define. Now the sketch. Yeah, somebody else was asking question, but let's just do it after plotting it. I mean, it will take hardly a few minutes. So let's just do that. Now 0, 1, 2, 3. Even though the previous case probability mass function is discrete variable defined only at discrete points, but our fx, the definition of which says px less than equal to x, this guy is reasonably continuous in the sense that it is supposed to be defined at all points in x, from minus infinity to plus infinity all the time. So this guy is defined at all points. Now I cannot say that I won't tell you, or I cannot ask question on what will be the cumulative distribution function at point less than 0 also. So maybe you are able to see something like a red dot now. So I'll have to plot this or sketch this at all points, because this has to be defined as probability x less than equal to small x. So let's see what you have defined for 0. For 0, this guy is going to take value 1 by 8. Now what this function is supposed to be doing, let's just between the points, let's just try to do it. At 1, this guy takes the value what? 3 by 8. Oh, sorry, 4 by 8. So let's just put 4 by 8. At 2, it takes the value 7 by 8. So let me just put my values little bit closer. So 4 by 8, and then you give something like a 7 by 8, and then something which 1. Okay, I mean, plotting this at those points, I guess, is rather simple. I just use that numbers, whatever you gave. So 1.07 over 8, 4 over 8, and 1 by 8. Plotting it in between is what is interesting. So can somebody tell me what should I do between 0 and 1? Should I join it by the straight line between the two? Should I put something else? Yeah, please go ahead.
No, sir. So it will be a staircase like. Uh,
It should go, what you are saying, a horizontal line, which should just
yes,
stop
sir.
before 1. And at 1, this guy has taken a value 4 by 8. And what should I do from 1 to 2?
Sir,
Sir,
same. Take a straight line for at 4 by 8.
Okay. And then continue like this. And then this guy continues forever, of course, till infinity. And again, this guy is doing the same thing just before this reaching 0. Now look at this function. This function is unlike PMF. In the PMF, I was not writing anything in between. But in the case of cumulative distribution function, I'll have to write it at each point. This is the reason why cumulative functions become very useful at times, because this give a complete description of whatever is happening. Although the same feature is there, I mean the same information is there in the probability mass function, but due to the definition only of those discrete points, people still start thinking about what to do between it. So several people try to write down, for example, in the probability also 0 at all points. In that case, we should just write down this point, that our px is non-zero at those points and it is 0 at all the points. So the simplest thing which you can remember is that you can give probability value 0 to all the points which are ill-defined, because these are ill-defined points, and hence any numerical value which can be given is 0. This is how you can think of, but do not plot it in your PMF. It's not correct to do that. On the other hand, in the CDF, feel free to do it. It's the way it is defined in terms of your random variable. Can I say that this random variable, number of heads, take 0.3 as the value? 0.3. Can I say or not?
Yes, sir. We can.
Yes, sir.
It will give one
Yes.
1.1.
So let's say we have toss of a coin and we are using random variable. I mean, this is the random variable which we are using, number of heads. So can I say that this value can be equal to 0.3? It's an absurd question. I mean, this doesn't mean anything. Why will
No,
it take
sir.
0.3? Either it is 1 or 0. But can I ask a question? What is the probability that this random variable takes a value less than or equal to 0.3? Now, this is
1 by 8.
interesting, because now I am talking about something that probability, okay, does any integer or a value which has non-zero PMF value, does this come here? And then you'll say, yeah, there exists something like 0 there, and hence I can write down. So this is the difference between your PMFs and the CDFs. The CDFs talk about x less than equal to, and hence we talk about the continuous distribution. PMFs talk about x strictly equal to, and hence we do not talk about anything which lies, let's say, for the discrete values, anything lies in between. But that is more of a philosophical, I mean, you can say about it. Whenever you have any doubt, put probability 0 everywhere other than the points at which it is defined. Okay, now what about this right continuous? Although I am sure that the plot itself has told you that. Let's look at this value, this at 0. What's the value if I approach this point from the right hand side? If you look into it, all the values were 1 by 8. So if I approach this f of 0 and I approach it from the right hand side, f plus, you will see that it was always taking this value 1 by 8 such that f0 is also 1 by 8. So this was a flat point. But what about if I approach this 0 from the left hand side? If I approach it from this side, this guy was taking the value
0.
0
0.
all the
0.
time. And this guy at f equal to 0 becomes 1 by 8. So it is not continuous from the left hand side, but it is continuous from the right hand side. This is what it means when I said the word right continuous, that the limit which is at f equal to 0, it remains if you approach it from the right hand side. But if you approach it from the left hand side, you will encounter a discontinuity. So the nature of the discontinuity is defined in the word right continuous, that from the left it may or may not be continuous, but from the right it will definitely be continuous all the time. So if you go from plus infinity to minus infinity, this function will always look continuous. If you go from minus infinity on the other side, this will not be there. So that's the interesting nature of this function. Now I will invite the questions before I proceed further.
Excuse me, sir.
Yes.
Sir, can you explain this example wherein you had taken x to be 0.3 again?
Oh yeah. What I was saying, that when a particular random variable is discrete, for example, the number of heads, if I ask you what is the probability that this random variable takes exactly the value 0.3, you will tell me, sir, this question is absurd in some sense, because this random variable is can take only discrete value. Of course you can put 0, there is nothing wrong, but the question in itself, look into it, the question is that this random variable can take only value 0, 1, 2 and 3, and I am asking you to give me the result for this random variable to take strictly the value somewhere in between, or maybe some the values which it cannot take. So the question in itself looks absurd to certain degree. On the other hand, if I ask you question, what is the probability that this random variable can take a value less than equal to 0.3, then this question doesn't fall under the absurd category, because there exists the probability which this random variable is going to take. And this is what the difference between a CDF, which is given by this expression, versus PMF, which is given by the other. And okay, I was just trying to explain why it is not good to define PMF at the points other than those points at which it is defined. So this is what I am saying, that generally, I mean, whenever you are asking number of heads and suddenly somebody asks, okay, give me the value, what is the chances that this random variable can take value 0.3? So you will, oh, please do not ask this kind of question, because this doesn't make any sense. For example, you are tossing a coin and asking somebody to say head or tail, and that person will say head, head, tail, tail, and you say, oh, what are you saying? I mean, either ask for head or for tail. I mean, I'm going to do one toss. So some sort of idea which is conveyed that PMF takes values at the finite points only, whereas the CDF takes values at all the points of X. These all are ideas which are important for the discrete random variables. For the continuous ones, you won't even worry about these things.
Okay, sir.
Does that make sense? Does that make sense? I mean, in some sense,
Yes, sir.
why do we define it like this?
Yeah, that clears it.
Yeah,
Thank you.
because I'm seeing the habit that students are regularly joining it like this, and this gives a problem because suddenly you are saying the probability here in between is non-zero. Yeah, you got the point, right? This red small dots.
Yes, sir.
That's a bad way of done. Okay. Any other question? Please go ahead.
Sir, this CDF function is kind of a graph which is represented by the step function.
Yeah, in this case, yes, something like that. But in the step function, it is a single step. So it's a staircase. It's not a unit step function. It is a staircase function in that case, I would suggest.
Yes, sir. I could relate it to that thing only. That's why I just asked.
Yep. Okay, some other definitions. One thing which becomes very important in the questions of probability is not to just find the probability less than equal to something or greater than equal to something, but also a question like what is the probability that a is less than equal to x less than equal to b. Now I am very careful in writing a strictly less than here. So x is strictly greater than a, but x is less than equal to b. The definition of the CDF becomes very useful in this case. You can do it from a very basic formula, but I am not deriving it here. That once you have the knowledge of CDF, you can also ask certain questions or you can answer certain questions related with what is the probability that a random variable lies between 2 points A and B. And that's rather simple. It can be given by just FB minus FA, where F is, of course, FB is the cumulative distribution function at point B and FA is the cumulative distribution function at point A. What if I ask you in that case a question, what is the probability of A less than equal to X less than equal to B? One more feature which will come.
So FB minus FA plus F is equal to A. FA, sorry.
Sir, FB minus FA plus PA.
Right. So
PA,
please
sorry.
see that it is important to remember that this is equal to Px equal to A union A less than X. This is from the first principle, right? You can always write it down like this. And X equal to A, this portion is disjoint with this portion where X is strictly greater than A. So I can always write down the probability as Px equal to A plus, remember the axiom, and this means Px equal to A plus Fb minus Fa. See from the definition. Now, what does that mean? It means that the probability of A less than equal to X less than equal to B may or may not be same as A less than X less than equal to B, depending on what this guy would be. In fact, as a homework, what I would like to give you, please think about what will be the case A less than equal to X, B, P. These are all the things which become very tricky in the discrete random variable. In the continuous random variable, things become rather straightforward. But still, we should be able to do it in both the cases. So let's just do it. So which other case which is left over? A strictly less than X, strictly less than B. Please give the formula for these also in terms of CDFs, FB minus FA. So take this as the homework for today's class.
The second one is FB minus FA minus PB.
Okay, and the first one will be adding Px equal to A to that, but then
Yes,
subtracting something to that. Okay, yeah, it's easy,
easy as it
straightforward.
Sir,
is
can we
not
Uh,
take
realistic like.
what is the takeaway point? Takeaway point is the probability of A less than X less than equal to B. One, it can be given from the CDF. That's one. And the second takeaway point is that it may or may not be same. These four things which I have written here, 1, 2, 3, and 4, may or may not be same in this discrete random variable. Okay. Yeah, questions here. If not, then I would like to quickly move. And now that we have the basic idea of this, then let's just quickly move to something what we call as the continuous random variable. So in this case, my random variable x will take continuous values. And hence, I define something as probability density function. So PDF, very common acronym, probability density function, PX, counterpart of PMF. But this PDF is defined in such a way that probability that a random variable x is going to take the value between x and x plus dx is equal to px times dx. Now, please see the difference with respect to the discrete case. There, the PMF was such that it was defining the probability. Pxk was defining the probability at certain points. PDF is, on the other hand, is defined in such a manner that Px dx, only when you multiply it by some sort of a distance or the variable dx, then it gives the probability. In itself, Px is not the probability. In itself, that's the use of the word density, that it is a probability density function, such that it will give us probability when multiplied by this interval dx. It will still follow the rules of the probability exactly in the manner in which we have, that this Px has to be greater than equal to 0 and minus infinity to infinity Px dx over the whole sample space. This has to give us the total probability 1. But the probability density function, the one major difference between the probability density function and the probability mass function is that probability mass function itself gives the probability, whereas the probability density function provides us the probability once we multiply it by dx. Although you guys know it because you remember that your psi x gives the some sort of amplitude and psi star psi. This guy gives probability density. When multiplied by this dx, this gives you the probability exactly like that. So probability density function for the continuous random variables are defined like this. Can somebody help me defining the cumulative distribution function for the continuous random variable, which is nothing but probability x less than equal to small x? How will it define?
So we'll take it from 0 till that point. Dx will be ranging from 0 to that point, x.
0?
No, sir, from minus infinity to x.
Yeah, I mean, in certain cases, it may be 0, right? But mostly you will take minus infinity to x, px dx. It is, if you can think of, it is the counterpart of the summation. So summation is now replaced by integration. Other than that, the limit is going from leftmost point of the x up to that particular point of it. So please see this guy. Now this gives me just one last point for the today's class. What about the probability at a given point in continuous random variable? So I define my Px in such a way, if you look into it, it's very intelligently defined, that it will give me the probability. But if I talk about the probability at a given point, then what should I what should be the value?
0.
0.
So
So
how will
dx.
you how do you get that 0?
So dx would be 0.
Yeah, I mean this is again interesting. Since small x is a continuous random variable, it will take the values which will be depicted by integers or something else in terms of the numerical function, numerical values. Small x.
Real numbers.
Sir, number, a real number.
Real numbers. So continuous random variable, that means that we are talking about the real number, right? This is where the x is lying. Now, real number has this interesting thing that if I talk about 0.3 as a real number, then 0.3, I mean, you can always think about, so maybe 0.4 is another real number, but then somebody will say, no, sir, I mean, there lies one real number more in between this 0.35, and another will say, no, sir, 0.351 is different from 0.352. So you should go to third place, and then the next person will say, sir, but this way you can continue forever. So what will be the place at which you are going to end? Figuring out that what is the exact value of the real number. It's very difficult because you'll have to continue specifying the points up to which you would like to go, and there also real number will not stop. There may be, you can again add some point after that. This is exactly the same problem which you get when you are using C programming language. Oh, our time is ended. I am just finishing off. When our, so if you define your variable as a floating point variable and then try to ask in this program if a particular floating point number takes exactly this value, and it cannot happen in C because that number can take any value up to 8 or 16 decimal point. So in this case, the important thing to note is that we do not talk about this point PDF at a given point. The consequence of which is what? The consequence of this is that for the case of continuous random variable, whether we write this or whether we write a less than equal to x less than equal to b, they are all same. So, I mean, I can also write the rest of the two, but this is another important point. Probability density function, since it is such that it will give us the probability in certain interval. So, four of those quantities which were different, which may be different in the discrete random variable case, p a less than x less than equal to b, etc., etc., they are same in the case of continuous random variable, and hence it is easy to write in the case of continuous random variable fb minus fa for all four of those. Whether you use this one, that one, doesn't matter. Okay, so I'll take rest of the things tomorrow. Questions here? Yes, no? So, okay, in that case, it is 11:06. So, if no questions today, then anyway, we are building the concepts, so we will use those concepts tomorrow. Fine, thank you. And what was the question? I mean,
Thank
there
you,
was
sir. Thank
some.
you, sir.
Sir, please
Thank
enter
you,
Thank
sir.
you,
the
Bye.
sir.
ID. Okay, yeah, this ID it should have been added. Okay, yeah, bye. Bye, guys.